I want to talk a little bit about the geometric sequence, which is a very specific, special type of sequence. This is not going to be a very long video with a detailed introduction and explanation of the properties of the geometric sequence. If you want that, you can find that online. What I want to do now is just call your attention to this particular sequence because it will be important later when we talk about series. But very briefly, a geometric sequence with first term a and common ratio r is a sequence that has this format. So basically, whenever an is a times r to the power n minus 1, then that will be a geometric sequence. We're going to say that a is the first term and that the common ratio is r. Basically, what this means is that if you plug in the numbers, n equals 1 gives you a times r to the power 0, which is just a. If n equals 2, then that's a to the power a times n to the power 1, because we're doing n minus 1, right? So this is ar. A3 will be ar squared, right? And then a4 is going to be ar cubed, and so on. So what's happening with each term is that we're taking the previous one and multiplying by r, which is why this is called a common ratio. If you likewise take any term and divide by the term that came before, you get r. So that is the meaning of this phrase, common ratio. What's interesting about this is that whenever the absolute value of the common ratio is less than 1, you're multiplying by something small. Just imagine multiplying by 0.5, for example. Then whenever you multiply by 0.5, that's the same as taking the half of the number. So this is going to be half of the previous number. This is going to be half of the previous number. This is going to be half of the previous number. So this is getting smaller and smaller. And so for sure, this is going to converge to 0 in that case. So it doesn't even have a choice as to where it's going to converge to. It will converge to 0 whenever the common ratio is less than 1 in absolute value. So that includes negative values as well. Negative 0.5, negative 0.7, 0.999, right? Something very close to 1, but still less than 1 will also make this converge. It's going to converge a little slower, but it is going to converge, and it is going to converge to 0, again, because numbers are getting smaller and smaller and smaller. If the common ratio is 1, nothing is happening. You're multiplying by r, but r is 1. Then this is a, and then a again, then a again, then a again. This sequence does converge, but it converges to a. It's just a constant sequence. So that will be a sequence, a list of numbers, a, all the time. In any other cases, this sequence will diverge. So the case that I list here as r equals negative 1 is interesting. A, negative a, negative a, negative a. This will also diverge because it will not approach in any specific number. It will be oscillating between negative a and a, with the exception, and I didn't write this down, but I'll write this here, unless a is 0 itself. If a is 0, then a and negative a are the same thing, and this sequence here is also the same as this. It's constant, but in any other case, when a is not 0, the sequence will diverge, okay? And also when a is an absolute, let me say it again, whenever r, an absolute value, is greater than 1, so r equals 2, r equals 3, whenever you multiply by r, you're going to be getting bigger and bigger numbers. So this sequence is going to be either diverging to positive infinity or to negative infinity, or even oscillating, getting huge negative numbers, huge positive numbers, sort of oscillating intuitively between positive infinity and negative infinity. That's not really the case, but you can think about it this way. So simple example here, can I find the limit of a sequence if it exists? Item A here, this is, I can say that it's geometric with common ratio 1. Excuse me, first term 1, common ratio 3. You can see that the terms of the sequence will be when n equals 1, I have 3. When n equals 2, I have 9, 27, 81, so on, right? Multiplying by 3 every time. This sequence has ratio that's bigger than 1 in absolute value. So the sequence diverges. The limit does not exist. It does not exist because the sequence diverges. It goes to positive infinity. Now the second sequence is not geometric per se. Bn equals 1 plus negative 1/2 to the power n. But if I consider dn equals negative 1 to the power n without the plus 1, dn is geometric with the ratio r is negative 1/2. Because absolute value r is less than 1, dn converges, and it converges to 0. So the limit of bn is going to be the limit of 1 plus dn. So it will be the limit of 1 plus the limit of dn. So it's 1 plus 0, which is 1. So we have calculated the limit. And then for C, we just have Cn equals, if I go back, negative 1 to the power n. So this sequence right here is geometric with the ratio negative 1, so it diverges as well. If you were to write the terms of this sequence, you're going to have negative 1, 1, negative 1, 1. It's never going to approach any specific number, so this sequence will diverge. Now, there are plenty of problems that you can solve, a lot of cool properties that geometric sequences have. For example, if you know that in a geometric sequence, let's say you know that A13 is 25 and A15 is, just make up a number, and sometimes it's going to look a little ugly. That's fine. Let's say A13 is 25, A14 is 15. We can find A14. So let me say it again. A13 is 25, A15 is 24. So can I find A14? In fact, I can, because I know that once I get to 25, that's A13. And this is A14 is not known, but A15 is known. And I know that to move from one term to the next, I have to multiply by r. So that means that I took 25, multiply by r, and then multiply by r again to get 64. And I can immediately find r here. R squared is going to be 64 over 25. So that means r is going to be 8 over 5. This is the common ratio. And so if I want to find the term here in the middle, A14 will be A13 times r. And so that will be 25 times 8 over 5, which is the common ratio. I cancel these out. And 8 times 5 is going to be 40, like this. This is also connected to this idea of the geometric mean. So the geometric mean of two numbers, let's say of numbers x and y, is the number that's the square root of x times y. And you can see that if you take the geometric mean of 25 and 64, it will be this number here in the middle. So if you plug it in, you will get that 25 times 64 is root 25 times root 64, which is 5 times 8, which is 40. So this is a very cool property, and that would be correct even if you had different terms, not the terms that are immediately here in the vicinity of A14, but if you move to A12, for example, and to A16, and you do the geometric mean of A12 and A16, you can also find A14. And as long as the two numbers that you're using are equidistant from the term you're trying to find, from the sort of center of your geometric sequence, you can always use a geometric mean to find that number in the middle. This also connects to the idea of an arithmetic sequence. Arithmetic sequences are sequences that behave like this. So instead of you have this first number and you multiply that or add that to n minus 1 times this number d, and that's, instead of calling the common ratio, that will be a common difference. And it has similar properties whenever we replace square roots by division by 2 and multiplication by addition. It has similar properties. This is not the goal here for us. It's good to have this type of sequence in mind. It would be something like this: a plus d, a plus 2d, a plus 3d. It's not one of our big goals because we want to talk about series later on, and arithmetic sequences don't behave really well when they turn into series. They will always diverge unless d equals 0 and a equals 0. But otherwise, the properties that you see for arithmetic sequences are similar. So it may be helpful for you to think about them when trying to remember everything that you need to remember if you've seen them before.